Okay. So my name is Max. I'm going to be talking about Rust smart contract APIs from the Near Protocol blockchain. So I'm not going to give you much of the introduction of what blockchain is and WASM is. So let's just jump right into the architecture. For most of the blockchains, the high-level architecture of the node is that you have a blockchain layer, you have runtime layer. Blockchain layer does stuff like network consensus, storing the blocks. It also exposes some RPC APIs, so it can act as a microservice. Runtime layer is what we're going to be focusing on today. And it has virtual machine for running your smart contract. And it has the smart contract code, and it also has a state storage. State storage is basically where you save the side effects of running the code on your virtual machine. There are basically two camps these days in the blockchain world. One of them is like, let's use a general purpose virtual machine like WASM. Well, today we also learned about RISC-V. And the general purpose language or like Rust or TypeScript. And another camp is like, no, let's write specialized virtual machine specifically for our blockchain and use specialized language. So there are obviously pros and cons in these two approaches. With WASM you have existing tooling, community, and it kind of passed the validation check by the community, meaning if the language existed for long enough, it's a good language, the features are polished also, right? It's also general purpose, means it's, you can write almost anything, Turing complete, can be viewed both as pros and cons. The specialized virtual machine, usually they fine-tune it to a specific blockchain. And in some cases, if it's like a functional language or non-Turing complete language, it allows formal verification, which is good. The problem is it's a niche language. Not many people know how to write in this language. And yeah, so our blockchain is in the WASM camp because we believe that WASM checks out all the checkboxes of being a good virtual machine for the blockchain. It was designed to be platform independent, check. Determinism, just don't use floats and you're good. Sandbox execution compilation, well obviously, you're going to be using LVM and crane lift, you're going to have bombs, so there are actual compilers there that are single pass compilers. They don't have bombs, and their code base is actually really small. One of them is written by Parity. It's called a Lightbeam, really good, fast compiler. And they have, the actual benchmarks matter a lot, Like every company has their own benchmarks according to some benchmarks, like Ethereum has their benchmarks of WASM, the overhead of running Rust compiled into WASM over the native, according to their benchmarks, is like 80%. So it's like plus 80%, 1.8 multiplier there. Small size of the compiled code, that was what WASM was designed for. You open the web page in a browser, WASM is getting sent over the network. Was optimized for the small compiled code size. And also close to machine code, which is good. Runs pretty fast. If you write smart contracts in Rust and compile them on the WASM, then you have some bonus features. Two of them I talked already about. It's existing tool in community, code transfer. Also you have memory safety with Rust. But also another one is zero-cost abstractions. So to remind you, zero-cost abstractions is like if you don't use feature, you don't pay for it. And even if you use feature, you couldn't have hard-coded it, like hand-coded it better yourself. And Rust prides itself of being very zero-cost abstraction-oriented language. So it has these iterators, futures, like CERDE, supposed to be all zero-cost abstractions. And like if you find some issue with iterators, like it 3x slower than a handwritten for loop, you should actually file a bug. So yeah, it's really good for the smart contracts because we want them to be small and efficient. So if you import the iterators from STD, it's almost as good as writing for loop yourself. There are existing blockchains out there that support smart contracts written in Rust. I have listed some of them. If I missed you, raise a hand. So the first one is our blockchain, Near Protocol. We have Rust API, which we call Near Bindgen for the lack of originality. Then we have Perlin. They have their blockchain called Wavelet. And also they call the Rust API just smart contract. Then we have eWASM. That's a really great team. They have created API not just for Ethereum, but for Ethereum-like blockchains, because they think there are going to be many of those. And Parity created Ink, which is not just Rust API, but also standard library for their Substrate Polkadot blockchain. And then Oasis, they have created Mantle. Nick here, I think in the audience, maybe he's gone already. He wrote Mantle. And then there is deprecated PWASM, which is Parity WASM plus Fleetwood, which is like a standard library for smart contracts. It was written for Core1 blockchain, which was the first blockchain to run WASM deprecated. So this is like a high-level architecture, which is similar for Rust APIs. You have WASM executor running Rust contract, and then it communicates with the blockchain layer, state storage, which I moved here separately through the contract interface and blockchain interface. So contract interface are basically exports of your smart contract, like what the functions that your contract exposes so that blockchain can call it, like deploy, deploy function is quite common. Then a blockchain interface are functions that blockchain allows the smart contract to call, like what is the current block index, what is the amount of money on the given account, what is the account ID. And here I kind of separated it into state storage and everything else, and we'll see why later. So here's an example of smart contract written in Ink. Ink is the eDSL, embedded domain-specific language, which means you can write a smart contract in Rust, but you have to follow certain rules. Like you need to have certain structure, you need to call certain macroses. So this is the example of smart contract that we're going to use throughout different APIs. It's incrementer. What it does, it just increments the value. It has like one value there, U32, and one function, increment. You call it, it increments the value by the given amount. It also logs it. So the contract interface here is a deploy function. That's what blockchain is going to call on the contract. Also, when you wrap it with this macro contract, then it's actually going to generate some functions that you don't see right now too. So it's also the part of the contract interface. The blockchain interface is what you can call on the blockchain. Like for instance, env print line. That's like a login function. That's how they expose blockchain interface. And then another part of the blockchain interface, the state part of it, is basically if you want something to be preserved as a state on the blockchain, wrap it with storage value, for instance. And then this value thing is like after you call this contract one time, next time it's actually going to be preserved. So that's the state part of the blockchain interface there. Unfortunately, it only works for some primitive types for now. So mental eDSL looks like this. You have different macro there, derive macro service. Then you pass an additional argument called context in each function that you want to be exposed as the smart contract function. And then instead of deploy, you have new. And then you also need to declare your own function main here. And you need to decorate with indexed the stuff that you want to be, I think, on the blockchain. And also you need a compiler plugin to actually compile it into WASM. So our thing, if we take the same contract in our Rust API, it's going to look like this. You just decorate it near bindgen. You need to derive default serialize, deserialize. You compile it. It runs on our blockchain. Behind the scenes, we're going to derive a whole bunch of code for you. Actually, our smart contracts, we not only allow Rust, we also allow TypeScript and Ethereum. So we want them to interop with each other. And they understand JSON. So what we're going to do behind the scenes is we're actually going to serialize, deserialize arguments and return values of your functions into JSON. But you're not going to see this because it's all hidden behind this procedural macro. We also have context similar to Oasis blockchain. And the state, we're just going to derive it for you. You're not going to see what we do there. But if you want like a fine-grained control, you can have it. Yeah, basically this slide explains what I just explained for you. Our special macro iterates over the functions. It looks at whether it's mutable, not mutable. It understands whether the state should be saved or not. Default, you can have your own deployment initialization function there if you want. There are other blockchain from Perlin that does pretty much the same except arguments. They are not. You have to pass them through the structure called parameters and then unpack them manually. So the big question is, can we unify all of them? Oh, because they kind of look similar, right? So contract interface, yes, straightforward. You have just some procedural macro that generates all the stuff for you, right? You need deploy, sure, you have a macro for deploy function, new, like you can generate all of them. With procedural macros, users do not even need to know that they expose some functions for the blockchain to, then the blockchain interface, that's the big question. And that's basically going to be the core question of this talk. And to answer this question, which we're going to answer at the very end, we need to go back in the history because we're going to learn from some mistakes that we've done in the past. And brief history of WebAssembly. It all started with mscripting. So there were some guys that were like, let's compile C++ and JavaScript for whatever reason. And they did it by introducing some hacks that were basically like annotations in JavaScript. It's a valid JavaScript that were emulating the type system, right? Then SpiderMonkey team from Mozilla noticed it, and they thought, we can actually utilize those hacked annotation to run our engine more efficiently. So they did more annotations, and that created Asm.js. And then what happens is when SpiderMonkey engine notices that it's an Asm.js and not just plain JavaScript, it switches to a completely different mode and executes efficiently. And it was so efficient that they were able to port Unreal Engine and like MySQL and all other kind of large programs to Asm.js and like run it efficiently in a browser. It was a huge success. Everyone noticed it. Large companies and organizations, especially those behind major browsers, noticed it. And the momentum of this success allowed them to get together and create a new standard better than Asm.js, which is WebAssembly. And the mscripting then also allowed to produce not just Asm.js, but if you want, you can compile it C++ into WASM plus some JavaScript glue code. So that's how you would run some program compiled into WASM with mscripting in the browsers. You have some WebAssembly module, and then inside the same WebAssembly module that you compile, you have some glue code. Because what happens is that if your C++ program accesses libc, and it like does the file read, this gets translated to the special ugly function called syscall3. And it is ugly because you have this which, you have two arguments here, which and var args. And var args is basically a blob of serialized arguments. So, not nice. And then JavaScript glue code wraps it all, exposes this syscall, and then unpacks them, and then knows what to do with them. Like, for instance, it does some local storage on the browser operations. So the big question is, like, how do we run it outside the browser? Because people wanted to do this. So they had some runtimes for WebAssembly. But now WebAssembly runtimes that will run in this WASM code that you would generate previously with the mscripting would have to emulate this glue code, the JavaScript glue code. They would have to expose the same functions here. And that was pretty bad, because now you have glue code there, emulation of the glue code there, so it's emulation of the emulation of POSIX. This thing is not strongly typed. This whole thing is not nice. And yeah, this is bad. This is like bad for two reasons. Two types of glue code there. Also no specialized interfaces. It's really hard to access DOM. And other things if you want to run it outside the browser. And so there came WASM system interface, WASI. And this is a very fresh effort that was announced early this year. Basically, the idea is, let's standardize all these imports that we had, but instead of ugly syscall3, we're going to have something nice looking that looks very much like libc. And we're going to have different modules for different tasks. Like core is basically going to mirror POSIX entirely, except processes. Processes are going to be outside because some systems just do not have processes, even if though they support POSIX. Then crypto and sensors and 3D graphics and even smart contracts were envisioned as separate modules in this WASI. So now if you write WebAssembly module in WASI and you like try to read from file, like here, you call this nice function, and then the WASI enabled WASM runtime will expose this function. That's it. Very nice, no glue code. However, some people still did not like it. There is a nice post by Ben Laurie, who is a security director from Google, with the title, How to Ruin a Perfectly Good Container, which is a critique of WASI. Well, it's mostly a critique of POSIX and the fact that many people continue emulating POSIX on systems where they actually don't need to emulate POSIX. And he criticizes POSIX. He says, like, POSIX was invented in the 60s, and the use case was completely different. There was a mainframe where multiple people would work on the same mainframe, and those people were all experts, and they would only run really simple programs that were easy to understand. So you know what the program was doing because it was simple. You just didn't trust people. So the threat model was different. We had untrusted tenants on your machine, but trusted software because it was so simple and so small. But these days, the threat model is different. The software is so humongous, you cannot understand what it is doing. If you want to somehow constrain it, you basically need to do it on a different level. But people are trusted because realistically, in most cases, the people who run code are those people who own the computer. I mean, in most cases, there is one user on the machine. And they're actually not sophisticated enough to read the source code, even if they were able to read hundreds of thousands of lines of code and understand what the hell it is doing. And the union of the protection now also changed. Previously, it was files. You just constrain users to their home directories. Now, we want it to be higher level and more like fine-grained data items, like entries in your contact list, keys in a keychain, like other things like that. So he argues that POSIX is not suitable for that. And he says that many containers go through this life cycle. First, they see that POSIX is like opens too many things. It's really hard to control. You know, with POSIX, if you can only have like either full access to the network or no access to the network. There is no fine-grained control. And so they put it in the container because they do not understand the code that runs in there, but they want to somehow constrain it. And then they're like, oh no, the old code doesn't run on this container. Like WebAssembly, we did not expose the file system. Let's emulate POSIX inside. So they emulate POSIX inside, and we're kind of back to square here. So there are some issues with POSIX that I already told you about, like either full or no network access. People want to run stuff on IT devices. Some of them don't have file systems. This file system-based security, in some cases, can be cheated, not abstract enough. So POSIX is an old standard. So what happened with WASI, I'm not sure because of this feedback or for whatever other reason, is that they took this WASI core module, which was mirroring POSIX, and they split it into multiple modules. Like, well, not split, they're gonna do this, it's a future effort. Like file system gonna be extracted random numbers and clocks. So the idea is to have human readable, simple, small APIs in each of the WASI modules, so that when user runs a program, they can understand that what they're granting as a permission to the program. Right, what about blockchain and WASI? Can we use WASI as a standard for the blockchain smart contracts? This is the world of the Rust smart contracts in a blockchain these days. And there's basically blockchains that do not emulate POSIX and do not just have some custom imports, do not try to fit into WASI. There is one blockchain that is trying to fit into POSIX and WASI. This is the Oasis. They are trying to emulate POSIX by being like, if you call inside smart contract like environment variable named block index, you are getting block index. So they basically access the blockchain interface through the environment variables. When they try to do cross-contract calls, they actually open the socket. And what happens is that inside this gets translated into actually not opening the socket, but like actually doing a smart contract call. So they emulate in POSIX, at least they're going to, with WASI core, which is going to be split. No, the problems with this emulating POSIX inside smart contract is that if you want to do some very simple thing, like let's save hash map onto the blockchain, you have to save it on a file. So you need to somehow either serialize it or have some format of saving into the file. And then inside the runtime that runs your smart contract and that exposes you a fake file system, it needs to reinterpret it and put it on the Merkleized tree, because most of the blockchains are using Merkleized trees or kind of hash trees for their state storage. So the problem with that, now we have again glue code here and there, just like with mscripton. We have glue code where we save structures that align perfectly with the Merkleized trees, but we save them into files, and then we have emulation of the glue code where we try to fit file system onto the Merkleized tree. So that's bad. Two types of the glue code. Portability is broken again, by the way, but now not because of the IoT devices, but because some blockchains might actually be stateless. As it turns out, Ethereum is seriously considering to have stateless smart contracts in 2.0. I'm not sure how it's going to work. Maybe they're just going to save the result of the execution, but not the state. So the big question is what happens to smart contracts that use file system and try execute on like Ethereum 2.0. Yes, so that's the problems with emulating POSIX on WASI. But the big other question is, can we use WASI at all? Can we have a general common standard, common denominator among all the imports that blockchains expose to Rust smart contracts? So just let's go through those imports that blockchain exposed to the smart contracts. So this is our NEAR protocol. It's like about 30 imports. About like a dozen of them are related to storage and iterating, like walking on the Merkleized tree because we want to utilize the properties of Merkleized tree and not just use it as the key value storage. Then a whole bunch of them are related to our synchronous cross-contract calls because we do them asynchronously and not synchronously because we're sharded blockchain, and it's really hard to do synchronous calls with sharded blockchain. And a bunch of them are related to like economics, hashing, and other things. This is the int from parity. They have synchronous calls because I think they happen only inside the dot of their polka dots. And the storage only exposes two functions. It works only like key value storage. Save key and value and get value by the key. Parallel goes a bit lower level. They work more with the blobs of data here. When you say send transaction, you pass the payload, and payload is a blob of data. And when you get the payload, you get the blob of data too. So they operate with blobs of data there. Ethereum 2.0 has two types of the API. There's low level and high level, at least in the plan. So low level API is what they use for what they call execution environment. So Ethereum 2.0, they have execution environment, which is just an additional layer of virtualization. It's like WASM, and then on the top of it, they can run either EVM or WASM or some other stuff. So they have two layers of virtualization there. And for that, they need a low-level API, which operates with blobs of data, because they don't know what the virtual machine is going to be running on top. So they just like pass it the blob of data. There are just 5 functions. And they have high-level API. Supposedly, I think for the WASM running inside the execution environment. So this is like the second layer of virtualization. It's like 33 of them, and they're very Ethereum specific. So the only thing that you can notice here, like common denominators, is some financial stuff like get my balance, which is also a very different variable for everyone. Some people use 128, some like I64. But also key value storage. That's what was repeated many times. So maybe we can extract key value storage and also cross-contract calls. But cross-contract calls are difficult because everyone has different take of cross-contract calls. So the idea of how we can unify it is that let's not push it. Let's keep our imports to ourselves, like everyone has different imports. And as we converge to the common denominator, we take things that seem to be common and extract them in WASI modules and start using those. So you saw this context and env kind of variables available in smart contract APIs. We just move some stuff from them into the WASI module. For instance, key value storage is the great candidate for moving out from into the WASI module. And as the time goes, we're going to be extracting more and more stuff and becoming more WASI-like, and maybe at some time in the future we're going to converge. So that's the solution. Start with extracting key value storage, wait some time more, maybe we're going to find more common denominators, and second step is unknown. That's the end of my talk. This is our team. We have 14 people, a bunch of them from Google, Facebook, some MemSQL. All kind of champions, medalists, and finalists of Top Coder, ICPC, and other competitions. These are all links. Questions?
Smart contract things, just catch in.